There is a specific kind of silence that exists only in the deep winter of the Russian interior. A physical weight of snow and ice that muffles the world and turns the landscape into a white, featureless void. In the year 1903, in the provincial town of Kaluga, roughly 100 miles southwest of Moscow, this silence was absolute, matching the internal world of a man sitting alone in a small, drafty wooden house on the edge of the Oka River. His name was Konstantin Tsiolkovsky, and to the local villagers he was a figure of pity and mild suspicion. The deaf schoolteacher who had lost his hearing to scarlet fever as a child and retreated into a private world of books and strange metallic models. They saw him walking by the river, muttering to himself, staring up at the gray, low, hanging clouds as if waiting for something to fall. But they did not know that inside that drafty house, under the flickering light of a kerosene lamp, this isolated, disabled man was drafting a prison sentence for the entire human race. He was not building a machine, for he had no funding, no laboratory, and no staff, nor was he welding steel or mixing volatile chemicals, but simply writing on sheets of cheap paper using the fundamental laws of motion established by Isaac Newton 2 centuries earlier. As his pen scratched across the paper, Tsiolkovsky was deriving a formula that would become an exercise in pure logic, a mathematical exploration of how a body might move through the vacuum of space where there is no air to push against and no friction to slow you down. As the variables began to align into a simple, elegant arrangement of velocity, mass, and exhaust speed, the blood must have drained from his face as he realized, perhaps before anyone else in history, that the universe had rigged the game against us. This equation, which would later bear his name as the Tsiolkovsky rocket equation, was not a map to the stars but a description of a cage, revealing a fundamental and unavoidable relationship between motion and mass that would haunt every engineer, every dreamer, and every astronaut for the next millennium. It stated with the cold authority of physics that the cost of leaving Earth is not linear but exponential, proving that gravity is not just a force that pulls us down, but a jealous jailer that demands a tribute we can barely afford to pay. In 1903, the same year the Wright brothers flew their fragile glider over the sands of Kitty Hawk for a few hundred feet, Tsiolkovsky proved mathematically that flying to the planets was a problem of an entirely different species. For while the Wright brothers conquered the air, Tsiolkovsky discovered the wall beyond the air. To understand the horror of what he found, we must strip away the romance of space travel and look at the brutal reality of mechanics, realizing that on Earth, if you want to go somewhere, you push against something, whether it is a car pushing against the road, a train against the rails, a ship against the water, or an airplane pushing against the air to generate lift. In all these cases, the environment helps you because the world provides the resistance you need to move. But in space, there is nothing. No road, no water, no air. Only the vacuum and the great indifferent nothingness. To move in a vacuum, you have to bring your own matter to push against, carrying mass in the form of propellant and throwing it behind you with as much violence as possible, adhering to Newton's third law that for every action there is an equal and opposite reaction. But here is the trap that Tsiolkovsky uncovered. The fuel you carry has weight and mass, and to lift that fuel off the ground you need energy, which requires burning fuel, but the fuel you are burning to lift the ship must also lift the fuel you are saving for later in the journey. And to lift that fuel you need even more fuel, and to lift that extra fuel you need yet more, creating a vicious compounding cycle like a snake eating its own tail, but the snake is growing larger with every bite. The equation dictates that for every kilogram of payload, every astronaut, every camera, every sandwich you want to send into the cosmos, you must pay a tax in fuel that grows not by addition but by multiplication, meaning the more you want to speed up, the more the universe demands you leave behind. This is the tyranny of the logarithm, implying that as you try to achieve higher and higher velocities, the returns on your investment diminish to near zero. So you can double the size of your rocket, triple the amount of fuel, and yet only gain a tiny fraction of extra speed. You are fighting a losing battle against the very mass of the vehicle you are building. And Tsiolkovsky realized that to send a single human being to Mars using the chemical fuels available in his time, or even the chemical fuels available in our time, would require a rocket of monstrous proportions, a mountain of explosive liquid to deliver a pebble of payload. There is an ancient legend that illustrates this horror of exponential growth better than any physics textbook, telling of a wise man who invented the game of chess and presented it to his king. The king, delighted by the game, offered the wise man any reward he desired, and the wise man asked for a simple payment in rice, placing 1 grain on the first square, 2 on the second, 4 on the third, and 8 on the fourth, asking the king to keep doubling the amount for each of the 64 squares. The king laughed, thinking the request was foolishly small, but as they began to count, the reality set in, for by the time they reached the end of the first row, there were only a few hundred grains. But by the halfway point, the amount was billions, and by the final square, the number of grains required was enough to cover the entire surface of the Earth in a layer several meters thick. The rocket equation functions exactly like that chessboard. But instead of rice, the currency is fuel, and instead of a king, the victim is humanity, because the squares on the board are units of velocity. And while getting a rocket off the launch pad is manageable, getting it to the moon moves you down the board where the requirements double and quadruple. To reach even a modest fraction of the speed of light using chemical rockets, you would need a fuel tank larger than the observable universe. A calculation derived directly from Tsiolkovsky's notebook proving that the mass of fuel required exceeds the mass of all the atoms in all the stars in all the galaxies we can see. And yet Tsiolkovsky was a cosmist who believed in the destiny of humanity, famous for writing that Earth is the cradle of humanity, but one cannot live in a cradle forever. A beautiful sentiment that paints a picture of a baby growing up and stepping out of the crib. But we rarely discuss the context of that quote, for Tsiolkovsky wrote it while staring at the math that proved the cradle was surrounded by high razor wire walls, knowing that leaving the cradle was not like learning to walk, but like trying to climb out of a deep pit while carrying a backpack that gets heavier with every step you take. For thousands of years, humans looked up at the moon and the planets and saw them as destinations, imagining that space was just an extension of the ocean waiting for our ships. But Tsiolkovsky showed that space is not an ocean. It is a gravity well, and we are at the bottom of it. To get out, we have to climb, and the energy required to climb out is fixed and non-negotiable. For physics does not care about our ambition or our bravery. It only cares about mass and velocity, demanding a toll paid in momentum. This realization transforms the history of the 20th century. For when we look at the Saturn V rocket, that towering cathedral of fire that took Apollo to the moon, we usually see a triumph of engineering and American ingenuity conquering the unknown. But look closer through Tsiolkovsky's eyes and you will see a skyscraper filled with kerosene and liquid oxygen weighing 6.5 million pounds at launch, yet delivering a tiny fragile lander that weighed a fraction of 1% of the launch mass to the lunar surface. The rest, the massive stages, the miles of piping, the millions of gallons of fuel, was all burned up and thrown away just to fight the equation, resulting in a ratio of rocket to spacecraft of roughly 500 to 1. That is not a triumph of efficiency, but a testament to brute force, humanity realizing we are trapped and deciding to smash our way through the prison wall with a sledgehammer made of fire. We succeeded briefly and touched the moon, but the cost was so high and the effort so monumental that we couldn't sustain it. So we retreated back to the cradle and haven't left since. The space shuttle never left low Earth orbit, and the International Space Station skims the top of the atmosphere barely 250 miles up, meaning in the grand scale of the solar system we haven't even made it to the sidewalk outside our house. Tsiolkovsky spent the rest of his life trying to find a way out of the trap he had discovered. filling notebooks with designs for airships, multi-stage rockets, and space stations, dreaming of ether settlements where humans could live in zero gravity, free from the crushing weight of the planet. He imagined a future where we would harvest the energy of the sun and become a stellar civilization. But the shadow of the equation never left him, because he knew that the initial step, the escape from Earth, was the hardest part. He famously said that the first step is difficult, dangerous, and requires a sacrifice, not knowing how right he was. For the sacrifice isn't just money or time, but the realization of our own insignificance. We are heavy creatures made of water and carbon and calcium, evolved in a 1G environment with bones and muscles tuned to the specific gravity of this rock. So to leave, we have to fight the very force that shaped us. To fight it, we have to bring the fire, which is why rockets are dangerous controlled bombs, requiring us to sit on top of millions of pounds of high explosives and light the fuse, because there is no gentle way to leave Earth. No elevator, only the violent, deafening roar of combustion screaming our way into the void. And even if we scream loud enough and build the biggest rockets our minds can conceive, the equation waits for us at the next destination, demanding we pay the tax again to slow down at Mars and pay it a third time to launch from Mars to come home. Every maneuver, every course correction, every change in velocity requires a sacrifice of mass, causing fuel tanks to get bigger and payloads to get smaller, shrinking the dreams of colonization from cities on Mars to a few people in a tin can trying not to die. The equation is relentless and follows us everywhere we go as the universal law of limitations, and while we might argue that technology advances with carbon fiber and supercomputers, this is the hubris of the modern age, confusing engineering with physics. Engineering can optimize and make tanks lighter or engines slightly more efficient, squeezing a few more percentage points of performance out of the system. But it cannot change the fundamental constants of the universe, the energy density of chemical bonds, or the gravitational constant of the Earth. We can polish the bars of the cage, but we cannot melt them, and this is the invisible cell made of math surrounding every planet, every star, and every galaxy, dictating that biological life is meant to stay put. The vast distances between the stars are not the problem is the weight of the shoes we are wearing. For we are trying to run a marathon in lead boots, and the faster we try to run, the heavier the boots become. This is the paradox that Tsiolkovsky handed to us, giving us the vision of the stars, and then the mathematical proof that they are almost impossible to reach. So where does that leave us? Are we doomed to stay in the cradle forever, destined to live and die on this single rock, watching the universe from behind the glass? To accept that would be to deny the very curiosity that defines us, and Tsiolkovsky didn't give up, and neither have we. For the last century has been a search for a loophole, a way to break the tyranny of the rocket equation by looking at the atom, the sun, and the very fabric of space-time. In the chapters that follow, we are going to explore the escape attempts, looking at the technologies that promise to shatter the walls of the prison, examining the terrifying power of nuclear propulsion, the ghostly efficiency of ion drives, and the impossible promise of antimatter. We will see how humanity has tried to outsmart the schoolteacher from Kaluga, but be warned that every time we think we have found a way out, the equation shapeshifts into a new problem, a new barrier, and a new danger, raising the price of leaving the cradle and changing the currency from fuel to something much more precious. If you have ever felt that the universe is too big or that we are too small, you have felt the shadow of the equation, the ghost in the machine of our civilization that explains why we are lonely in the cosmos. But understanding the trap is the first step to escaping it. For Tsiolkovsky wrote the sentence, but he left the pen on the desk, leaving it up to us to see if we can write a pardon or if the sentence is truly for life. Tonight we have merely defined the walls of our cell, feeling the cold draft of the Russian winter and hearing the scratch of the pen that sealed our fate. But the story moves from Kaluga to the deserts of New Mexico, the launch pads of Florida, and the deep radioactive silence of the outer solar system. We have defined the problem, and now we must examine the failed solutions. Looking at the moment humanity decided that if chemistry wasn't enough, we would ride the apocalypse itself to the stars. If you are ready to face the monsters of propulsion, the engines that spit death to create life, and the sheer overwhelming scale of the challenge that lies ahead, then verify your subscription, because the algorithm, much like the rocket equation, requires input to sustain momentum. Like this video to fuel the signal and prepare yourself, for the chemistry is about to fail, and the physics is about to get violent as we move from the prison of the mind to the tyranny of the exponent. Sleep well, or don't sleep at all. The choice is yours. To understand the true scale of our imprisonment, we must look at the greatest machine our species has ever constructed. It stood on Launch Complex 39A at the Kennedy Space Center, a towering obelisk of white metal gleaming under the Florida sun. To the crowds watching from the beaches, the Saturn V was a symbol of hope, a chariot that would carry men to the moon. But to a physicist, the Saturn V was a monument to despair. It was 363 feet of physical evidence that the universe does not want us to leave. Let us strip away the patriotic paint and the romantic nostalgia of the Apollo era to look at the anatomy of this beast with the cold, unfeeling eyes of the rocket equation. The rocket weighed 6.5 million pounds at liftoff. It was a cathedral of engineering, a skyscraper capable of flight. Yet of that immense weight, the structure itself, the aluminum tanks, the engines, the miles of complex wiring, the flight computers accounted for only a tiny fraction of the mass. The payload, the 3 astronauts, their life support, the command module, and the lunar lander accounted for even less. In fact, fully 96% of the Saturn V was nothing but fuel, and the tanks to hold it. It was not a vehicle in the traditional sense, it was a flying bomb, a controlled explosion waiting to happen, guided by a computer with less processing power than a modern musical greeting card. When the 5F-1 engines at the base of the first stage ignited, they consumed 15 tons of fuel per second. 15 tons. In the time it takes you to blink, the Saturn V burned through a quantity of kerosene and liquid oxygen equivalent to the weight of 3 African elephants. The violence of this consumption was necessary because the rocket was fighting a war on 2 fronts. It was fighting the gravity of the Earth, which pulled down with a relentless 1G of force, anchoring the massive structure to the pad. And it was fighting the rocket equation, which demanded that to lift the fuel for the upper stages, the lower stages had to be gargantuan. The acoustic energy generated by the launch was so intense that it could melt concrete and kill a human being standing a mile away simply by the pressure waves vibrating their internal organs into jelly. This was not elegant travel. This was a brute force assault on the laws of physics. We were screaming our way into the sky, clawing for every inch of altitude by throwing millions of pounds of matter behind us. The efficiency of this system, when viewed through the lens of interstellar ambition, was pitiful. Of the 6 million pounds that left the launch pad, only about 100,000 pounds made it to the moon. That is a payload ratio of roughly 1.5%. Imagine for a moment that you wanted to fly from New York to London. You buy a massive Boeing 747, you fill it with fuel, you fly it across the ocean, and then, upon arrival at Heathrow, you throw away the entire airplane. You crash it into the runway, destroying the fuselage, the wings, the engines, and everything inside. The only thing that survives the journey is the pilot's seat. That is the economic reality of chemical rocketry. It is an act of waste so profound that it borders on madness. We build these magnificent, complex machines, masterpieces of human ingenuity, and we burn them up in minutes just to deliver a tiny sliver of metal to a destination that is astronomically speaking right next door. And yet this was the only way the math allowed us to escape. The chemical bond, the energy released when atoms exchange electrons, has a hard limit. Nature does not allow us to extract more energy from kerosene than the laws of thermodynamics permit. We hit the ceiling of chemistry in the 1960s, and we have not broken through it since. This brings us to the Mars trap, the delusion that keeps modern billionaires and visionaries awake at night. We often hear them speak of colonizing the red planet, of building cities in the dust of Tharsis, of fleets of starships ferrying thousands of colonists to a new home. They show us shiny renders of glass domes and green valleys, but they rarely speak of the gear ratio. In logistics, the gear ratio determines how much effort is required to move a load. In space travel, the gear ratio is determined by the rocket equation. For every kilogram of supplies you want to land on the surface of Mars, every solar panel, every hydroponic tray, every liter of water, every breathing mask you need to launch roughly 5 to 7 kilograms into low Earth orbit first. But the problem compounds backwards. To get that 5 to 7 kilograms into low Earth orbit using chemical rockets, you need to burn 20 to 50 times that mass on the launch pad. The supply chain stretches back to Earth in a terrifying pyramid of consumption. To build a self-sustaining city on Mars using chemical propulsion would require a launch cadence that defies industrial capacity. We would need to launch a Saturn V class rocket every single day for decades. We would need to mine, refine, and burn oceans of fuel. The atmosphere of Earth would choke on the exhaust long before the first city on Mars was finished. The sheer mass of the propellant required to move a civilization across the void is a wall that no amount of optimism can breach. The chemical bond is simply too weak. It is a dead-end technology. It is a technology for flags and foot-on foreigns, for brief heroic visits where we plant a piece of cloth and run home before we run out of air. It is not a technology for migration. If we stay married to fire, if we continue to rely on the combustion of fluids to move us, we die in the cradle. We will never be an interplanetary species. We will simply be a species that visits its neighbors and then retreats to the safety of the shore. Consider the space shuttle, the machine that promised to make space travel routine. It was supposed to be a truck, a reusable workhorse that would lower the cost of orbit and open the heavens to commerce. But the space shuttle was still a chemical rocket. It was still bound by the same tyranny as the Saturn V. It required a massive external tank and 2 solid rocket boosters, essentially giant fireworks, to lift the orbiter. And even then, it could only reach low Earth orbit, a mere 250 miles up. It never went to the moon. It never went to Mars. It circled the Earth, trapped in the gravity well, burning billions of dollars to haul cargo to a station that was barely outside the atmosphere. The Space Launch System, NASA's new giant rocket, is just a remix of the shuttle technology. It is bigger, yes. It is powerful, yes, but it is still burning hydrogen and oxygen. It is still playing the same losing game against the rocket equation. We are polishing a steam engine and hoping it will take us to the moon. We are refining the horse and buggy and hoping it will cross the ocean. The fundamental problem lies in the exhaust velocity. This is the speed at which the gas leaves the engine nozzle. In the rocket equation, this variable is the only thing that can save us. If you can make the gas go faster, you can use less fuel. You can flatten the exponential curve. But chemical rockets are limited by the speed of sound in the hot gas. The molecules can only move so fast. The combustion of hydrogen and oxygen produces water vapor that expands at a maximum of about 4.5 kilometers per second. That sounds fast. It is 10 times faster than a rifle bullet, but compared to the orbital velocity required to stay in space 8 kilometers per second, and the escape velocity required to leave Earth 11 kilometers per second, it is barely enough. We are trying to achieve Mach 25 speeds with an engine that struggles to produce Mach 12 exhaust. The only way to make up the difference is to stack stages on top of stages, to discard empty tanks, to shed weight like a desperate climber cutting off his own ropes to reach the summit. This is why our rockets look the way they do. This is why they are tall, thin cylinders. They are mostly tank. The payload is an afterthought. The human being is an afterthought. The rocket does not care about the cargo, it cares about the fuel. The fuel is the passenger, the fuel is the pilot, the fuel is the mission. We are just along for the ride, squeezed into the tiny space left over at the top, praying that the controlled explosion beneath us does not become an uncontrolled one. The chemical rocket is a majestic, awe-inspiring, and ultimately tragic machine. It is the pinnacle of the industrial age, the ultimate expression of the internal combustion engine. But it is also a trap. It has convinced us that we are a spacefaring civilization because we can send a few people to the moon once in a generation. But that is an illusion. We are not spacefaring. We are barely space visiting. We are like a fish that has learned to jump out of the water for a few seconds. We see the sky, we feel the air, and we think we can live there. But gravity always pulls us back down. The water is our home. The air is a hostile environment that we can visit but cannot inhabit. Chemical rockets give us the jump, but they do not give us the flight. To truly fly, to truly swim in the cosmic ocean, we need to abandon the chemical bond. We need to stop rearranging electrons and start looking deeper. We need to find a force that is millions of times stronger than fire. But as we stand on the launch pad watching the smoke clear and the fire fade, we must admit the hard truth. For all our genius, for all our bravery, we are still using the same basic technology that the Chinese invented 1,000 years ago when they packed gunpowder into bamboo tubes. We just built bigger tubes. And until we find a way to break the chemical chains, the planets will remain points of light in the sky, beautiful, beckoning, and forever out of reach. The illusion is complete. The fire burns bright, but it burns out too fast. And when the fire is gone, the cold reality of the distance remains vast and unconquered. And so the silence returns to the launch pad. The echoes of the Saturn V fade into history, leaving behind a legacy of glory and a warning of limitation. We pushed chemistry to its absolute limit. We squeezed every ounce of energy out of the periodic table. And it wasn't enough. It got us to the doorstep, but it couldn't open the door. The moon is a graveyard of landing stages and crashed probes, a testament to the high cost of the journey. Mars is a graveyard of failed missions. The chemical age of spaceflight, for all its thunder and fury, has hit a wall made of mass, a wall made of energy density. If we want to go further, if we want to cross the Black Ocean to the other islands, we need a new kind of ship. We need an engine that doesn't just push. We need an engine that screams. We need to leave the safety of the campfire and touch the heart of the sun itself. But to do that, we have to be willing to play with forces that can destroy us as easily as they can save us. We have to be willing to trade the risk of explosion for the risk of radiation. The chemical illusion is over. The atomic reality is about to begin. If fire cannot take us to the stars, if the chemical bond is too weak and the tanks are too heavy, we must look for other ways to move. We must abandon the roar of combustion and seek a quieter, more efficient path. We must stop trying to overpower the rocket equation with brute force and start trying to negotiate with it. This brings us to the second era of propulsion, the era of the particle and the atom. It is an era defined by a ghost, deep in the vacuum of space, far from the thunder of the launch pad. A different kind of engine has been quietly proving itself. It does not scream like a Saturn V. It does not shake the ground. In fact, if you were standing next to it in the void, you would hear nothing but the hum of electricity. You would see only a faint, eerie blue glow, the color of a spirit trailing behind the spacecraft. This is the ion drive. If a chemical rocket is a scream, an ion engine is a breath. The principle behind it is fundamentally different. Instead of burning fuel to create heat and pressure, an ion thruster uses electricity generated by solar panels or a nuclear battery to strip electrons from a gas, usually xenon. This process creates positively charged ions. The engine then uses a magnetic or electrostatic field to accelerate these ions out the back of the spacecraft at tremendous speeds. The exhaust velocity of an ion engine is its superpower. While chemical rockets struggle to reach 4.5 kilometers per second, an ion thruster can easily propel particles at 40, 50, or even 90 kilometers per second. This 10-fold increase in efficiency completely transforms the mathematics of the rocket equation. It means you can get much more velocity for every ounce of fuel you carry. You do not need a tank the size of a skyscraper. You can carry a modest supply of xenon gas compressed into small canisters and still achieve impressive changes in speed over time. But the universe demands a balance. You can have high efficiency or you can have high thrust. You cannot have both. An ion engine is incredibly efficient, but its push is feeble. The thrust produced by a typical ion engine is roughly equivalent to the weight of a single sheet of paper resting on your hand. Imagine trying to push a car with the force of a sheet of paper. At first, nothing happens. The car does not move, but in the frictionless environment of space, there is no resistance. There is no air drag. There is no friction from the road. If you keep pushing with that tiny force, that single sheet of paper, second after second, hour after hour, day after day, the spacecraft will eventually begin to drift. Then it will glide. Then it will race. The acceleration is agonizingly slow, accumulating over months and years. The Dawn spacecraft, launched by NASA in 2007, used ion engines to explore the asteroid belt. It did not blast off with a surge of G-force. It spiraled slowly outward, its engines glowing with that signature blue light. Dawn accelerated continuously for years. It became the first spacecraft to orbit two different extraterrestrial bodies, Vesta and Ceres, maneuvering with a grace and fuel efficiency that chemical rockets could never match. It did the impossible, but it took its time. It was the tortoise of the cosmos. It won the race against gravity, but only because the race was very, very long. For a robotic probe with infinite patience, for a machine that does not breathe, does not eat, and does not age, this is acceptable. A robot can sleep for a decade while the ion drive gently pushes it toward Jupiter. But for a human crew, for biological entities with a shelf life, the ion drive is a death sentence of boredom. We are creatures of metabolism. We consume resources every second we are alive. We need air, water, food, and sanity. A propulsion system that takes 5 years to spiral out of Earth's orbit and another 10 years to reach Mars is useless to us. We would starve before we arrived. We would go mad from the isolation. The ion drive solves the fuel problem, but it fails the time problem. It offers us the solar system, but only if we are willing to spend our entire lives in transit. And for the stars, it is even worse. An ion drive could theoretically reach a nearby star, but the journey would be measured in millennia. Generations of humans would be born and die in the blue glow of the engine, forgetting what Earth looked like, forgetting why they left. The efficiency is a trap. It saves mass, but it costs time, and time is the one resource we cannot manufacture. So the pendulum swings back. We need efficiency, yes, but we also need power. We need an engine that has the high exhaust velocity of the ion drive, but the high thrust of a chemical rocket. We need a hybrid beast. We need to tap into the fundamental binding energy of matter itself. This desperation led us to the dreams of the atomic age, when humanity briefly flirted with the idea of riding nuclear fire to the stars. In the 1960s, while the public was watching the Apollo missions, engineers in the deserts of Nevada were building a secret. They were building an engine that did not burn. It screamed with the fury of the atom. This was the NERVA program nuclear engine for rocket vehicle application. The concept was elegant and terrifying. Instead of a combustion chamber where fuel and oxidizer mix and explode, a nuclear thermal rocket uses a solid core nuclear reactor. The propellant is liquid hydrogen kept at temperatures near absolute zero. This hydrogen is pumped not into a fire but through the core of the reactor. The uranium fuel rods, glowing white hot with fission energy, heat the hydrogen instantly to thousands of degrees. The hydrogen expands explosively and shoots out the nozzle. Because hydrogen is the lightest element in the universe, it can be accelerated to much higher speeds than the heavy water molecules produced by chemical rockets. The exhaust velocity of a nuclear thermal rocket is double that of the best chemical engine. Double. In the tyranny of the rocket equation, doubling your efficiency is not a small step, it is a revolution. It changes the exponent. It flattens the curve. A mission to Mars that takes 9 months with chemical rockets could be done in 3 or 4 with nuclear thermal. The mass ratio drops from an impossible mountain to a climbable hill. We built these engines. We tested them. In Jackass Flats, Nevada, the NERVA engines roared to life, spewing radioactive exhaust into the desert air. They worked. They were stable. They were ready to fly. NASA had plans to put a nuclear stage on top of the Saturn V. It would have taken us to Mars by 1980. It would have opened the outer solar system to human exploration. We could have had bases on the moons of Jupiter by the turn of the millennium. But we lost our nerve. The fear of radiation, the political fallout of the Cold War, and the shifting budget priorities killed the program. We took the most promising technology of the 20th century, put it in a crate, and buried it in the sand. We chose to stay slow. We chose to stay heavy. But let us assume, for the sake of the argument, that we revive NERVA. Let us assume we build the nuclear thermal rocket. Does it solve the prison? Does it unlock the stars? The answer, tragically, is no. Even NERVA, with all its power, is still a prisoner of the equation. Doubling the efficiency is great for the solar system. It makes Mars accessible. It makes the asteroid belt reachable. But for interstellar space, it is meaningless. Alpha Centauri is 4 light-years away, that is 24 trillion miles. A nuclear thermal rocket might get you up to speeds of maybe 20 or 30 kilometers per second. That is fast. It is faster than Voyager. But at that speed, the journey to the nearest star would still take 40,000 years. 40,000 years. That is the span of time separating us from the Stone Age. If a crew left Earth today on a nuclear thermal rocket, by the time they arrived at Alpha Centauri, human civilization on Earth might have risen and fallen 10 times over. The language they speak would be dead. The species might have evolved. They would arrive as ghosts from a forgotten past. The difference between a chemical rocket taking 70,000 years and a nuclear rocket taking 40,000 years is academic to a human being. Both are eternities. Both result in the crew dying of old age before they have left the Oort cloud. The hare is faster than the tortoise, but the race is so long that both of them die of exhaustion on the starting line. This is the cruelty of the scale. We think that if we make our engines twice as good, we can go twice as far. But the distance to the stars is not twice as far as the distance to Mars. It is hundreds of thousands of times farther. The gap between the planets is a stream, the gap between the stars is an ocean. And our nuclear engines, for all their heat and danger, are just slightly better rafts. We are trying to cross the Pacific on a log, and we are celebrating because we upgraded to a slightly more buoyant log. The rocket equation laughs at our incremental improvements. It demands a paradigm shift. It demands that we stop thinking in terms of kilometers per second and start thinking in terms of the speed of light. To bridge the gap between stars, we do not need to double our speed. We need to multiply it by 1,000. We need to move not at 20 kilometers per second, but at 20,000 kilometers per second. We need to reach a significant fraction of light speed. And to do that, we need to abandon the idea of controlled release of energy. The ion drive is too gentle. The nuclear thermal rocket is too restrained. We need violence. We need to tap into energy densities that make uranium fission look like a matchstick. We need to harness the forces that destroy cities. This realization forces us into a dark corner. We have exhausted the safe options. We have exhausted the clean options. The tortoise has failed because it is too slow. The hare has failed because it is too weak. If we want to escape the prison, we have to stop being polite with physics. We have to get dirty. We have to look at the bomb not as a weapon, but as a motor. The next step in our journey takes us away from the elegant laboratories and the silent vacuum chambers. It takes us to the drawing boards of the Cold War, where madmen and geniuses dared to ask the question, what if we stopped trying to build an engine and just ride the shockwave of the apocalypse? The era of the pulse is waiting. The era where we detonate our way to the stars. It is the most audacious, dangerous, and metal concept ever devised by the human mind, and it might be the only way out. But before we light that fuse, we must accept that the gentle blue light of the ion drive was a beautiful dream that lured us into a false sense of progress. It showed us we could move efficiently, but it hid the truth that efficiency is not enough. In the deep dark, patience is not a virtue. It is a slow form of suicide. If you are feeling the weight of the years pressing down on you, if the idea of a 40,000-year journey makes your chest tighten with the claustrophobia of the cosmos, then you are beginning to understand the trap. The universe is not just big, it is old, and it waits for no one. We are fleeting sparks trying to cross an eternal night. If we want to make it to the other side before we flicker out, we need to burn brighter. We need to burn harder. If you are ready to leave the slow lane and enter the realm of brute force physics, make sure you are subscribed. The next chapter is going to be loud, it is going to be radioactive, and it is going to challenge everything you think you know about what is safe in space travel. Like this video to verify your clearance and prepare for ignition. The tortoise is retiring. The dragon is waking up. If we cannot be fast and we cannot be efficient, we must be violent. We have tried the gentle path. We have tried the whisper of the ion drive and the controlled heat of the nuclear thermal rocket. Both failed to break the chains of the rocket equation because they lacked the sheer, overwhelming power required to bridge the abyss between stars. The distances are simply too vast for politeness. To cross the light years in a human lifetime, we need to stop asking the laws of physics for permission and start demanding it. This realization brings us to the most audacious, terrifying, and metal chapter in the history of human engineering. It brings us to the drawing boards of the Cold War, where a group of chain-smoking physicists dared to ask a question that sounds like the setup to a dark joke. What if we propelled a spaceship by detonating nuclear bombs behind it? This was not a fringe theory cooked up by madmen in a basement. This was Project Orion, a serious government-funded program in the late 1950s. The team included some of the most brilliant minds of the 20th century, including the legendary Freeman Dyson. They looked at the energy density of a nuclear warhead, a device designed to erase cities, and saw a packet of portable sunlight. They realized that a nuclear explosion is the most efficient way to release energy that humanity has ever discovered. If you could harness that force, if you could ride the shockwave of the apocalypse, you could shatter the limits of chemical and thermal propulsion. You could build a ship that didn't just crawl to the planets, you could build a ship that kicked the door down. The design of the Orion spacecraft was brutal. It abandoned the sleek aerodynamic lines of traditional rockets. It looked like a battleship, a squat, ugly tower of thick steel and graphite. At its base, there was no delicate nozzle, no complex plumbing. Instead, there was a massive plate of steel, the pusher plate, coated in oil to prevent it from vaporizing. The mechanism of flight was pure, unadulterated violence. The ship would eject a pulse unit, essentially a small directional nuclear bomb, out the back. The bomb would drift a safe distance behind the ship, roughly 200 feet, and then detonate. In the vacuum of space, a nuclear explosion does not create a blast wave of air like it does on Earth. Instead, it vaporizes the bomb casing and a surrounding propellant disk into a rapidly expanding cloud of superheated plasma. This plasma, moving at incredible speeds, would slam into the pusher plate. Bam! The ship would be kicked forward, then another unit would be ejected. Bam! And another bam! A heartbeat of nuclear fire driving the vessel faster and faster. To keep the crew from being turned into jelly by the forces of these repeated impacts, the pusher plate was attached to the rest of the ship by a series of gigantic shock absorbers, colossal pneumatic pistons that would smooth out the nuclear kicks into a steady, thrumming acceleration. It was a pogo stick riding on hellfire. The calculations for Project Orion were shocking. Unlike chemical rockets, which are 90% fuel and struggle to lift their own weight, an Orion ship would be incredibly powerful. It could lift thousands of tons of payload. It could carry a crew of hundreds. It could be built with heavy radiation shielding, libraries, and hydroponic gardens. Most importantly, it offered the holy grail of spaceflight: high thrust and high efficiency. An advanced Orion ship, powered by hydrogen bombs, could theoretically reach velocities of up to 10% of the speed of light. 10%. That is 18,600 miles per second. At that speed, the solar system shrinks to the size of a neighborhood. You could reach Saturn in weeks. You could reach Pluto in months. And theoretically, you could reach Alpha Centauri, our nearest stellar neighbor, in 40 years. A single human lifetime. A crew could depart Earth in their 20s, watch the sun fade to a star, and arrive at an alien system in their 60s. It was the first and perhaps the only technology ever conceived that placed the stars within human grasp using materials we actually possessed in 1965. We had the steel. We had the shock absorbers. We certainly had the bombs. We could have built it. We could have been a star-faring species by the 1980s, but we didn't. Project Orion was killed not by physics, but by a collective failure of nerve. The idea of launching a ship loaded with thousands of nuclear warheads was simply too terrifying. The fallout from the launch alone would have poisoned the atmosphere. The risk of an accident during ascent, a ship full of nukes crashing back to Earth, was a nightmare scenario. And finally, the Nuclear Test Ban Treaty of 1963 forbade nuclear detonations in space. We chose safety over the stars. We put the blueprints in a vault, disbanded the team, and went back to the clean, slow chemical rockets of NASA. We chose the illusion of safety over the reality of the distance. But even if we had built it, even if we had accepted the radiation and the risk, Project Orion had a hidden flaw. A flaw that brings us back to the relentless tyranny of the rocket equation. The flaw is the stopping problem. It is easy to forget in the excitement of acceleration that in space there are no brakes. If you accelerate to 10% of the speed of light, you are moving with the kinetic energy of a planet, killer asteroid. To stop at Alpha Centauri, you cannot just coast. You have to turn the ship around and fire the engines in the opposite direction to slow down. This means you have to carry enough nuclear bombs not just to speed up, but to brake. The rocket equation creates a mirror image of the launch requirements at the arrival point. If you need a mass ratio of 20 to get up to speed, you need a mass ratio of 20 squared 400 to get up to speed and then stop. The fuel requirements explode exponentially. An Orion ship designed for a one-way flyby is massive. An Orion ship designed to stop in orbit is monstrous. It would need to carry millions of nuclear pulse units. The ship would be so heavy that we would effectively have to mine the entire Earth of its uranium just to build one vessel. The industrial scale required to build a fleet of interstellar Orions exceeds the economic output of our entire civilization. We are not just fighting gravity, we are fighting the limits of our planet's crust. So if fission, the splitting of atoms, is too dirty and the fuel is too heavy, we turn our eyes to the cleaner, more powerful cousin fusion. This is the engine of the stars, the process that powers the sun. In the 1970s, the British Interplanetary Society launched a theoretical study called Project Orion to see if a fusion-powered starship was possible. The resulting design was a Leviathan. Orion would be a two-stage spacecraft weighing 54,000 tons, comparable to a fully loaded aircraft carrier constructed in orbit. It would be powered by inertial confinement fusion. The engine would fire pellets of frozen deuterium and helium, 3 into a reaction chamber 250 times a second. Their high-powered electron beams would zap the pellets, compressing them until they ignited in a miniature thermonuclear explosion. A powerful magnetic field, the magnetic nozzle, would then direct the resulting plasma out the back of the ship. The scale of Daedalus was humbling. It was designed to reach Barnard's star, nearly 6 light years away. The ship would accelerate for 4 years continuously, burning through tens of thousands of tons of fuel until it reached 12% of the speed of light. At this speed, it would cross the void to Barnard's star in 50 years. But Daedalus highlighted the critical flaw in all rocket designs, even fusion ones, the fuel source. Helium-3. The magic ingredient for clean fusion is incredibly rare on Earth. It is almost non-existent. To fuel a single Daedalus mission, we would need to mine the atmosphere of Jupiter for decades to harvest enough of the isotope. We are trying to bottle a star, but the bottle is the size of a city and the gas is on another planet. The infrastructure required just to fuel the ship is harder to build than the ship itself. And Daedalus was a flyby probe. It had no ability to stop. It would scream past Barnard's star at 12% of light speed, gathering data for a few hours before hurtling into the endless black. To make it stop, to make it a crude vessel, the mass would balloon to millions of tons. The fusion dream hits the same wall as the fission nightmare. The energy is there. But the mass of the machinery required to harvest, contain, and release it creates a ship so heavy that it can barely move itself. This problem, the problem of carrying your own fuel, led to one final desperate concept in the realm of nuclear propulsion, the Bussard ramjet. Proposed in 1960 by physicist Robert Bussard, this idea attempts to bypass the rocket equation entirely. Bussard looked at the empty space between stars and realized it wasn't truly empty. The interstellar medium is filled with hydrogen atoms floating in the dark, roughly 1 atom per cubic centimeter. It is a vacuum by terrestrial standards, thinner than the best laboratory vacuum we can create on Earth. But over the vast distances of space, that dust adds up to a lot of potential fuel. Bussard's idea was to build a ship that doesn't carry a fuel tank. Instead, it harvests fuel as it flies. The ship would deploy a magnetic field of immense proportions, a funnel stretching thousands of kilometers ahead of the vessel. This invisible magnetic web would scoop up the stray hydrogen atoms from the interstellar medium, funneling them into a reactor at the back of the ship. There, the hydrogen would be compressed and fused to generate thrust. It is the cosmic equivalent of a jet engine, which takes in air from the atmosphere to burn fuel. But the ramjet takes in the universe itself. The beauty of the Bussard ramjet is that it has no theoretical top speed limit imposed by fuel mass. Since you are picking up fuel as you go, you never run out. You could accelerate indefinitely. You could keep the engines running at 1g1 Earth gravity of acceleration for years. According to the math of relativity, if you could maintain a 1g acceleration, you could cross the galaxy in a single human lifetime. The ramjet promised the stars without the burden of the tank. It became a staple of science fiction, the golden standard for how humanity would become a galactic civilization. But the universe, as always, is cruel to our dreams. As physicists looked deeper into the mechanics of the ramjet, they discovered a fatal flaw: the drag. To catch enough hydrogen from the incredibly sparse interstellar medium, the magnetic scoop has to be enormous, thousands of miles wide. But when you plow a magnetic field that size through the gas of space, even thin gas, it creates resistance. The hydrogen atoms don't just politely enter the intake, they interact with the field, creating friction. Calculations revealed that as the ship gets faster, the drag from the scoop increases faster than the thrust from the engine. The magnetic funnel essentially acts as a giant parachute. The faster you try to go, the harder the universe holds you back. Instead of accelerating to light speed, the ramjet would hit a terminal velocity, choking on the very fuel it was trying to eat. Furthermore, the hydrogen found in deep space is mostly proton standard hydrogen 1. Fusing solitary protons is an incredibly slow and difficult process, the same process the sun uses, which takes billions of years. To work in a spaceship engine, we need deuterium or tritium, which are rare isotopes. So the ramjet would have to act as a refinery, sifting through endless cubic light, years of useless protons to find the rare gems of heavy hydrogen, all while fighting the drag of the medium. The elegance of the design collapsed under the weight of particle physics. We are left with a landscape of wreckage. The chemical rockets are toys. The ion drives are toys for tortoises. The nuclear pulse ships are monsters that we are too afraid to build, and even if we built them, they are too heavy to stop. The fusion ships require mining Jupiter. The ramjets are choked by friction. We have scaled the ladder of known physics, from the campfire to the atom. And at every rung, we have found a locked door. The impossible scale of the universe seems to have defeated the impossible scale of our engineering. But there is one rung left on the ladder. One final substance that sits at the very edge of reality. It is not a fuel in the traditional sense. It is the mirror image of matter itself. It is the most volatile, expensive, and dangerous substance in existence. If nuclear fusion is the power of the sun, this substance is the power of the Big Bang. It is the only thing that offers a theoretical exhaust velocity of light speed. It is the ghost that haunts the equations of quantum mechanics antimatter. We have saved the most seductive mirage for last. Antimatter promises to solve everything. It promises infinite energy density. It promises a ship that can fly on a few grams of fuel. But as we will see in the next chapter, the antimatter mirage is the cruelest trap of all. It lures us in with the promise of perfection, only to reveal an economic and containment nightmare that makes mining Jupiter look easy. We are about to find out that the ultimate fuel comes with the ultimate price tag. If you are enjoying this descent into the impossible, if the sheer scale of the engineering challenges is making the universe feel bigger and darker, then verify your subscription. We are moving from the realm of dirty steel and nuclear fire to the realm of magnetic traps and gamma rays. The stakes are getting higher, the fuel is getting more unstable, and the prison walls are looking thicker than ever. Like this video to keep the reactor stable and join us for the next dive. The dragon of fusion has failed. The demon of antimatter is waiting. We have reached the end of the line for conventional matter. The chemical rockets are too weak. The nuclear thermal engines are too slow. The pulse ships are too heavy. The fusion drives are choked by the friction of the interstellar medium. Every attempt to burn matter to move matter has hit the wall of the rocket equation. But there is one final substance that sits at the very edge of reality. A substance that promises to break the rules by rewriting the definition of energy itself. It is not a fuel in the traditional sense, it is the mirror image of existence. It is the ghost that haunts the equations of quantum mechanics. It is the most volatile, expensive, and dangerous substance in the universe, antimatter. We have saved the most seductive mirage for last. To a physicist, antimatter represents the absolute ceiling of propulsion efficiency. It is the holy grail. To understand why, we must look at how we extract energy from matter. When we burn kerosene in a Saturn V, we are breaking chemical bonds, releasing about 1/1000th of the mass as energy. When we split a uranium atom in a nuclear reactor, we are converting about 1/10 of 1% of the mass into energy. Even in a fusion reaction, the engine of the stars, we are only converting about 7/10 of 1% of the mass into energy. The rest is just ash, waste, and dead weight that the ship has to drag along. But antimatter is different. When an atom of antimatter meets an atom of normal matter, they do not burn. They do not split. They annihilate. They vanish completely, converting 100% of their mass into pure energy, obeying Einstein's famous equation EMC, squared with terrifying literalism. There is no ash. There is no smoke. There is only a flash of gamma rays and high-energy particles moving at the speed of light. The efficiency is perfect. It is the maximum theoretical limit of physics. A single gram of antimatter, an amount roughly the size of a paperclip colliding with a gram of normal matter, would release 43 kilotons of explosive energy. That is 3 times the yield of the bomb that destroyed Hiroshima. A handful of this stuff could boil an ocean. A few kilograms could power a civilization. And a few tons? A few tons could push a starship to 90% of the speed of light. The design of an antimatter rocket is a study in magnetic confinement and brinkmanship. You cannot hold antimatter in a tank made of steel or titanium or diamond. If the fuel touches the walls of the container, the ship explodes. Instead, the antimatter must be suspended in a vacuum, held in place by powerful magnetic fields, floating in a state of perfect levitation. This device is known as a penning trap. When thrust is needed, the magnetic fields release a microscopic stream of anti-protons into a stream of normal protons. They annihilate, creating a swarm of short-lived particles called pions. These pions move at nearly the speed of light. A magnetic nozzle, an invisible funnel of force, directs these particles out the back of the ship. The exhaust velocity of such an engine would be a significant fraction of light speed itself. This solves the rocket equation in a single stroke. With an antimatter engine, you do not need a mass ratio of thousands or millions. You could carry a fuel supply the size of a suitcase and fly to Mars in weeks. You could carry a supply the size of a shipping container and fly to Alpha Centauri in a decade. The math is beautiful. The physics is sound. It seems that we have finally found the key to the prison cell. The barrier of mass has been dissolved by the power of annihilation. But if the physics of antimatter is a dream, the economics is a nightmare. Antimatter does not exist naturally in our universe. We cannot mine it from asteroids. We cannot scoop it from the atmosphere of gas giants. It seems that shortly after the Big Bang, for reasons we still do not fully understand, the universe chose matter over antimatter. There are no antimatter galaxies waiting to be harvested. To get it, we have to make it, and making it is the most inefficient industrial process in human history. We manufacture antimatter atom by agonizing atom and particle accelerators like the Large Hadron Collider at CERN in Switzerland. We smash protons together at nearly the speed of light, and in the debris of those collisions we occasionally find a stray anti-proton. We capture it, slow it down, and carefully store it in a magnetic trap. The rate of production is agonizingly slow. CERN, the pinnacle of human engineering, produces roughly 10 nanograms of antimatter per year. A nanogram is 1/1000th of a gram. At this production rate, to accumulate a single gram of antimatter would require 100 million years of continuous operation. To produce the kilogram required for a small interstellar probe would take 100 billion years, roughly 7 times the current age of the universe. The fuel of the future is effectively unobtainable in the present. We are trying to fill a swimming pool with a pipette that drips once every century. And the cost is astronomical. Estimates suggest that a single gram of antimatter, if we could even produce it, would cost roughly $62 trillion. That is more than the entire global economy. To fuel a starship with tons of the stuff would require an economy larger than the combined Outhanchpout of human history. This brings us to the fundamental misunderstanding of antimatter. It is not a fuel source, it is an energy storage medium. It is a battery. Because we have to create it using energy, we can never get more energy out of it than we put in. In fact, due to the inefficiencies of particle accelerators, we have to put in about 1 billion times more energy than we get out. We are not discovering a new oil well. We are building a battery that costs $1 billion to charge just to get $1 of electricity back. To build an antimatter starship, humanity would first have to build a Dyson swarm, a vast array of solar collectors around the sun to generate the titanic amounts of energy needed to run the particle accelerators. We would have to become a Type 2 civilization just to make the fuel to become an interstellar one. The infrastructure burden is simply shifted from the ship to the factory. The rocket equation is defeated, but the energy equation takes its place, and it is just as unforgiving. But let us assume we solve the production problem. Let us assume we have the Dyson swarm and the factories churning out kilos of anti-hydrogen. We load it onto the ship. Now we face the storage problem. You are launching a ship carrying the most volatile substance in existence. A chemical rocket can sit on the pad for days. A nuclear reactor can be turned off. But antimatter is always on. It is always waiting for a single mistake. A power failure in the containment magnets. The ship vaporizes. A computer glitch that lets the field waver. The ship vaporizes. A micrometeoroid impact that punctures the vacuum chamber. The ship vaporizes. We are essentially trying to build a fireplace for a fuel that hates existence. The level of reliability required for an antimatter containment system on a 40-year voyage is beyond anything humanity has ever engineered. We cannot build a toaster that lasts 10 years without breaking. How can we build a magnetic trap that holds a kilogram of pure destruction stable for a century in the harsh radiation environment of deep space? The crew of an antimatter ship would be living on top of a bomb that is actively trying to explode every single microsecond. The psychological stress alone would be unbearable. And finally, there is the gamma ray problem. When matter and antimatter annihilate, about half the energy comes out as neutrinos, which pass right through the ship and provide no thrust. The other half comes out as gamma rays and charged pions. Gamma rays are light. They are incredibly hard to reflect. You cannot build a mirror for gamma rays. They just punch through the material, heating it up. This means that a significant portion of the energy you created doesn't go into pushing the ship. It goes into cooking the ship. You need massive shielding to protect the crew and the magnetic coils from the radiation of your own engine. This shielding adds mass, heavy mass, lead and tungsten. Suddenly, the rocket equation returns with a vengeance. You saved weight on the fuel, but you gained weight on the engine and the shielding. The perfect mass ratio begins to slip away. The ship gets heavier. The acceleration drops. The dream of light speed fades back into the reality of a long, slow cruise. Antimatter is a mirage. From a distance, it looks like a shimmering oasis of infinite velocity. But as you get closer, you see the price tag, the danger, and the shielding requirements. It is not the key to the prison. It is just the most expensive way to stay inside. We have now exhausted every option for carrying fuel. We have looked at chemistry, fission, fusion, and annihilation. Each one has failed to give us the stars. Each one has hit a limit imposed by nature. The Tsiolkovsky rocket equation stands undefeated. It seems that as long as we insist on carrying our engine and our fuel with us, we are doomed to crawl. The mass penalty is simply too high. But what if we changed the rules? What if the mistake is the rocket itself? What if we stopped trying to carry the fuel? What if we left the engine on Earth? This is the radical shift in thinking that defines the final frontier of propulsion. If the ship is too heavy, make it light. Make it lighter than air. Make it lighter than a feather. Build a ship that is nothing but a sail and push it with a wind made of light. This is the concept of beamed propulsion. It promises to bypass the rocket equation entirely. It promises to send tiny wafer-thin probes to Alpha Centauri in a single human generation. It sounds like the solution we have been waiting for. But as we will see in the next chapter, leaving the engine behind creates a new set of problems. It turns space travel from a vehicle challenge into an infrastructure challenge. It requires building lasers the size of countries, and it introduces the terrifying problem of the one-way ticket. A ship pushed by a laser on Earth can go very fast, but it has no way to stop. It is a bullet fired into the dark, destined to fly past the stars without ever landing. We are about to enter the era of the light sail, the era of the star chip. It is our last best hope. But like all hopes in the mathematical prison, it comes with a catch. If you are still here, staring into the gamma-ray flash of the annihilation engine, you are beginning to understand the depth of the trap. The universe does not give up its secrets easily. It demands energy scales that frighten us and time scales that mock us. But we are stubborn. We are not done yet. If you want to see what happens when we try to ride a beam of light to the stars, verify your subscription. We are done with fuels. We are done with tanks. We are about to turn the lights on. Like this video to charge the laser banks. The antimatter mirage has faded. The laser highway is waiting. We have reached a breaking point. We have tried to carry the fire with us, and the fire is too heavy. The chemical rockets are choked by the weight of their own tanks. The nuclear engines are choked by the weight of their shielding. The antimatter drives are choked by the weight of their containment systems. The Tsiolkovsky rocket equation stands like a monolith, blocking every path that relies on internal propulsion. It seems that as long as a ship has to push itself, it will never go fast enough to matter. The mass penalty is absolute. But what if we changed the rules of the game? What if the mistake isn't the fuel, but the location of the fuel? What if we could leave the engine at home? This radical question births the concept of beamed propulsion. It suggests that we should stop building rockets and start building kites. If we leave the heavy power plant, the reactor, and the fuel tanks on Earth, the spacecraft itself can become a ghost. It can be a gossamer sheet of reflective material, weighing only a few grams, carrying a payload the size of a microchip. And instead of pushing itself, it is pushed by a beam of light sent from home. This is the dream of the solar sail, evolved into the laser sail. It promises to bypass the rocket equation entirely by removing the mass variable from the flight vehicle. The physics is sound. We have known for centuries that light carries momentum. Photons have no mass, but they have a punch. When a photon strikes a mirror and bounces off, it transfers a tiny amount of kinetic energy to that mirror. It is a microscopic push. But if you have enough photons, billions upon trillions of them, and if the mirror is light enough, that push becomes a shove. We have tested this. The Japanese spacecraft Ikaros unfurled a 14-meter solar sail in 2010 and successfully accelerated using nothing but sunlight. It proved that you can sail the vacuum, but sunlight is weak. The pressure of the sun at Earth's distance is equivalent to the weight of a feather on a football field. It creates a gentle drift, not a relativistic sprint. To reach the stars, we need a storm. We need to replace the sun with something brighter. We need lasers. This is the premise of Breakthrough Starshot, the most ambitious interstellar project currently on the drawing boards. The plan calls for building a massive array of phased lasers on Earth, or perhaps on the high plateaus of the Atacama Desert. This array, the beamer, would combine the Outhenschfout of millions of fiber optic emitters into a single coherent column of light. The power Outhenschfout would be staggering roughly 100 gigawatts. That is equivalent to the Outhenschfout of 100 nuclear power plants, focused into a beam the width of a few meters. The target of this beam is the star chip. It is a fully functional space probe shrunk down to the size of a postage stamp. It carries cameras, navigation sensors, communication lasers, and a tiny radioactive battery. Attached to this chip is the light sail, a mirror roughly 4 meters wide, made of a material thinner than a soap bubble but stronger than steel. The launch sequence would be the most violent event in the history of acceleration. The laser array would fire for just a few minutes. In that brief window, the pressure of the laser light hitting the sail would subject the tiny probe to tens of thousands of Gs of acceleration. It would go from a standstill to 20% of the speed of light, roughly 7,000 miles per second in less than 10 minutes. At this velocity, the journey to the Alpha Centauri system would take just 20 years. A single human generation. A scientist could launch a fleet of these star chips early in their career and be alive to receive the data when they arrive. The fleet would streak across the void, silent and cold, powered by a push that happened decades ago. As they approached the destination, they would awaken. Cameras would spin up. They would fly through the alien solar system, snapping pictures of Proxima b, the potentially habitable planet orbiting our nearest neighbor. Then they would beam the data back to Earth using a tiny onboard laser. 4 years later, humanity would see the first close-up image of an alien world. The beauty of the light sail is its purity. It turns interstellar travel from a survival mission into an infrastructure project. We can build the power plant on Earth where mass doesn't matter. We can maintain it, fix it, and upgrade it. We can use it to launch thousands of probes, creating a highway of light to the stars. It seems we have finally cheated the prison. We have found a way to be fast without being heavy. But the light sail has a fatal flaw, a tragedy written into its very design. It has no brakes. A spacecraft pushed by a laser from Earth can accelerate brilliantly. But once it reaches its destination 20 years later and 4 light years away, there is no laser at Alpha Centauri to push back. There is no beam to slow it down. The star chips would not stop. They would flash through the target system at 1/5 the speed of light, traversing the distance from the planet to its sun in minutes. They would have mere moments to gather data before hurtling out the other side, exiting the system forever into the endless black of the galactic void. They are tourists who cannot stop the car, snapping photos out the window as they scream past the Grand Canyon at supersonic speeds. For a robotic probe, a flyby is acceptable. Better to see for a minute than never to see at all. But for a human crew, this is a non-starter. You cannot launch a colony ship at relativistic speeds if you cannot stop at the New World. To stop a human crewed light sail, you would need a laser array waiting for you at the destination. But to build that array, you would have to send a slow ship there first to construct it. It is a causality loop. You need the infrastructure to get there, but you need to get there to build the infrastructure. Some have proposed hybrid solutions. They suggest using a magnetic sail or magsail to drag against the interstellar medium. By generating a massive magnetic field, the ship could create friction against the thin hydrogen gas of space, bleeding off velocity over decades. It would be a long, slow deceleration, drifting into the target system like a ship dropping anchor in a storm. But even with these theoretical breaks, we are still facing the problem of scale. Breakthrough Starshot works because the payload is a gram. If we want to send a human, a biological entity that weighs 70 kilograms and requires tons of water, food, air, and radiation shielding, the math explodes again. To accelerate a human ship to 20% of the speed of light using lasers, the beamer array would need to be the size of Texas. It would require more energy than the human race generates in a year, released in a few minutes. The beam would be so powerful that if it accidentally drifted across a satellite or a city, it would vaporize them instantly. We would be building a Death Star laser on the surface of our own planet. The atmospheric distortion would scatter the beam, meaning we would likely have to build this mega structure in orbit, hauling millions of tons of mirrors and emitters into space using chemical rockets. We are back to the beginning. The infrastructure burden simply shifts the impossible mass from the ship to the launch pad. And let us look at the sail itself. The material requirements are borderline magical. The sail must be 99.999% reflective. If it absorbs even a tiny fraction of the laser's energy as heat, it will vaporize instantly. When you hit a thin sheet of material with 100 gigawatts of power, almost perfect isn't good enough. It has to be perfect, and it has to survive the journey. For 20 years, the sail will be bombarded by interstellar dust. At 20% of the speed of light, a grain of sand hits with the force of a bullet. By the time the ship arrives, the sail would likely be tattered, riddled with holes, and useless for any deceleration maneuvers. So the light sail is a partial victory. It gives us eyes on the stars, but it does not give us feet on the ground. It allows us to send postcards, but not people. It is the ultimate probe technology, but it leaves the biological species trapped on Earth. We can look, but we cannot touch. The prison walls have become transparent, but they are still solid. We can see the universe through the glass, but we cannot open the door. This brings us to the end of the fast options. We have tried everything. We have tried burning fuel. We have tried splitting atoms. We have tried fusing hydrogen. We have tried annihilating antimatter. We have tried riding light beams. And every single path has led to a dead end of physics or economics. The universe has spoken. It has set a speed limit that is effectively zero for massive objects on cosmic scales. We are not meant to go fast. But if we cannot go fast, does that mean we cannot go at all? There is one option left. It is the option that requires us to abandon the obsession with speed and embrace the horror of time. If we cannot cross the galaxy in a human lifetime, perhaps we should stop measuring the journey in lifetimes. Perhaps we should build a ship that is not a vehicle but a world, a ship that drifts, a ship that takes 10,000 years to reach the stars, a ship where the people who arrive are the great-great-great-grandchildren of the people who left. We arrive at the concept of the generation ship. This is the idea that saves science fiction writers when they realize the warp drive is impossible. It sounds noble. It sounds like a solution. It solves the fuel problem by accepting a slow, drifting trajectory that requires minimal energy. But the rocket equation is not so easily cheated. When you slow down to save fuel, you increase the duration. And when you increase the duration, you trade the problems of physics for the problems of biology. You are trading propellant mass for life support mass. And as we are about to discover, biology is the heaviest, messiest, and most fragile thing in the universe. We are about to enter the biological anchor. We are going to look at what happens when you lock a population of humans in a metal box for 1,000 years. We are going to see that while metal can survive the void, society cannot. The entropy of the closed system is coming for us. We have exhausted the technological tree. Now we must climb the sociological tree. And the fruit there is bitter. The generation ship is not an ark. It is a tomb in the making. If you have followed us this far, you have seen the death of the rocket and the birth of the laser. You have seen the impossible scale of our ambition. Now we turn inward. We turn to the soft, squishy reality of the human animal. If you think physics is hard, wait until you see psychology. The final trap is not the engine, it is the mind. If you are ready to explore the madness of the long voyage, the mutinies of the deep dark, and the terrifying evolution of a species in isolation, verify your subscription. We are done with lasers, we are done with beams. We are about to lock the airlock for the last time. Like this video to seal the hull. The light sail has flown past. The generation ship is drifting into the dark. We have reached the point of surrender. We have banged our heads against the walls of physics for 6 chapters. We have tried to go fast with chemicals, with atoms, with antimatter, and with light. And every time the Tsiolkovsky rocket equation has slapped us down. The energy required to move a ship to the stars in a human lifetime is simply too great. The mass penalties are too severe. The infrastructure is too vast. The universe has set a speed limit for massive objects that makes interstellar travel, for all practical purposes, impossible for a biological species that lives less than a century. So if we cannot change the physics, we must change the biology. If we cannot cross the void in a lifetime, we must stop measuring the journey in lifetimes. We must stop trying to be sprinters and start trying to be glaciers. We arrive at the final desperate concept of interstellar colonization, the generation ship. This is the idea that saves science fiction writers when they realize the warp drive is a fantasy. It is a vessel designed not for a crew but for a civilization. It is a city in flight. A hollowed-out asteroid or a spinning cylinder miles long, creating its own gravity through rotation. Inside there would be forests, lakes, fields of crops, and a population of thousands. They would depart Earth knowing they will never see the destination. They are the seeds. They will live, reproduce, age, and die in the void. Their children will take over the watch. And their children's children. For centuries or perhaps millennia, the ship will drift through the interstellar dark, a tiny bubble of life preserving the flame of humanity until it reaches a new sun. It sounds noble. It sounds like a solution. It solves the fuel problem by accepting a slow, drifting trajectory that requires minimal delta V. We don't need to reach light speed, we just need a gentle push and 10,000 years of patience. But the rocket equation is not so easily cheated. When you slow down to save fuel, you increase the duration of the mission, and when you increase the duration, you must increase the mass of the life support system. You are trading propellant mass for biological mass, and as we are about to discover, biology is the heaviest, messiest, and most fragile thing in the universe. We are about to learn that keeping a human alive is infinitely harder than building a rocket engine. To understand why, we must look at the laws of thermodynamics, specifically the concept of entropy. Life is a process that fights entropy. It is a localized rebellion against the disorder of the universe. To stay alive, a human body must take in organized energy, food, water, oxygen, and expel disorganized energy, heat, carbon dioxide, waste. On Earth, this is easy. Earth is an open system. We have a massive fusion reactor, the sun pouring free energy onto us every day. We have a massive atmosphere to disperse our heat. We have oceans and soil to absorb and recycle our waste. The biosphere does the heavy lifting for us for free. On a spaceship, you are in a closed loop. There is no free lunch. There is no way to throw your trash. Every molecule of oxygen you breathe must be recycled from the carbon dioxide you exhale. Every liter of water you drink must be reclaimed from your urine, your sweat, and the humidity of your breath. Every calorie of food you eat must be grown in soil that is fertilized by your own waste. You are living inside a machine that must function as a perfect planetary ecosystem, but without the buffer of a planet size. Technophiles and futurists will tell you that we can build machines to do this. They point to the International Space Station, which recycles about 90% of its water. They say, look, we are already doing it, but 90% is a death sentence on a 1,000-year voyage. If you lose 10% of your water every cycle, your tank runs dry in a decade. For a generation ship, the efficiency must be 99.999%. You cannot lose a single atom. And here is the horror: we have tried to build closed ecological systems on Earth. We have tried to play God in a bottle. And we failed miserably. In the Arizona desert in the early 1990s, humanity conducted the most ambitious biological experiment in history. It was called Biosphere 2. It was a magnificent glass cathedral, sealed off from the outside world. Inside, it contained a rainforest, an ocean with a coral reef, a mangrove wetland, a savanna, a fog desert, and a farm. 8 people, 4 men and 4 women, were locked inside for 2 years. The goal was to prove that humans could create a self-sustaining world, a prototype for a Mars colony or a generation ship. It was supposed to be a triumph of systems engineering. It became a nightmare of biological collapse. Within months, the system began to drift out of equilibrium. The oxygen levels plummeted mysteriously. The crew began to suffer from sleep apnea and fatigue, gasping for air like mountain climbers at 14,000 feet. It turned out that the concrete used to build the habitat was absorbing the oxygen, a chemical reaction the designers hadn't anticipated. The carbon dioxide levels spiked, causing the ocean to become acidic, killing the coral. The pollinators, the bees and hummingbirds, died off, so the crops failed to reproduce. But while the beneficial species died, the pests thrived. The cockroaches and ants exploded in population, infesting the kitchen, the bedrooms, and the farm. Morning glory vines and invasive species choked out the food crops. The crew was starving. They lost an average of 16% of their body weight. They were suffocating. And they were trapped in a glass cage where the very air they breathed was turning against them. They had to inject oxygen from the outside just to keep them alive, breaking the seal and invalidating the experiment. Biosphere 2 proved that we do not understand the complexity of our own planet. We cannot replicate the delicate balance of Earth even when we are sitting on Earth. To try to replicate it in a metal box, drifting in the absolute zero of deep space with no hope of rescue, is an act of hubris that borders on suicide. A generation ship would face problems that Biosphere 2 never dreamed of. The primary problem is the leak. No seal is perfect. Every valve, every airlock, every joint in the hull leaks a tiny amount of atmosphere. Over a timeline of centuries, these microscopic losses add up to tons of air and water venting into the void. A generation ship would slowly bleed to death. To counter this, you would need to carry vast reserves of water and ice, increasing the mass of the ship, which brings us back to the rocket equation. You need more fuel to push the reserves, which makes the ship heavier, which requires more fuel. The cycle of mass captures us again. And then there is the problem of mechanical entropy. A metal bolt can last for 1,000 years in a vacuum, but a pump cannot. A filter cannot. A computer chip cannot. On a ship that travels for 10 millennia, every single component will break, rot, or fail. The crew must be able to manufacture every single part of the ship from scratch. They need mining equipment to harvest asteroids for raw materials. They need smelters, foundries, and chip fabrication plants. The ship cannot just be a vessel. It must be a fully industrial civilization. The complexity of such a system is staggering. A modern Boeing 747 has 6 million parts. A generation ship would have billions. If critical systems fail, say, the water recycling plant or the air scrubbers, the colony dies in days. There is no FedEx in deep space. There is no backup. The maintenance debt of a generation ship would consume the lives of the crew. They wouldn't be explorers, they would be mechanics, enslaved to the machine that keeps them alive, spending every waking hour fixing leaks, soldering wires, and patching the hull. But the physical decay of the ship is nothing compared to the biological decay of the passengers. We often forget that evolution does not stop just because you leave Earth. In fact, it accelerates. A small population, isolated from the main gene pool of humanity, subjected to cosmic radiation and a completely artificial environment, will change. This is the concept of genetic drift. In the high radiation environment of interstellar space, DNA mutation rates will increase. Most mutations are harmful cancer, birth defects, organ failure. The ship's medical facilities would need to be advanced genetic engineering labs just to keep the human genome stable. But over thousands of years, the environment will select for new traits. The gravity on the ship might be lower than Earth's. The light levels might be different. The carbon dioxide levels might be higher. The beings that arrive at Proxima Centauri might not be human anymore. They might be frail, spindly creatures with large eyes adapted to the dim light of the ship, unable to stand in a gravity field, unable to breathe natural air. They might have lost their immunity to Earth's bacteria. They might have developed a culture, a language, and a morality that is utterly alien to the Earth that sent them. They might look back at the recordings of their ancestors and see monsters. The generation ship solves the rocket equation by sacrificing the very thing it was meant to save, humanity itself. And let us consider the microbiology. A human body is not just a single organism. It is a colony of trillions of bacteria. We carry a microbiome that digests our food and protects our skin. On a generation ship, this microbiome would evolve too. In the closed loop of the ventilation system, bacteria and viruses would circulate endlessly, mutating and adapting. A common cold virus could evolve into a lethal plague in the stagnant air of the ship. A harmless gut bacteria could turn into a flesh-eating pathogen. The crew would be locked in an eternal biological arms race with their own germs in a space smaller than a shopping mall. The romantic image of the Ark floating among the stars is a lie. A generation ship is a rotting garden. It is a dying lung. It is a desperate struggle against the second law of thermodynamics, fought in a coffin of steel. The biological anchor is the heaviest anchor of all. We are not designed for the void. We are designed for a biosphere that spans an entire planet with weather, seasons, and tectonic renewal. To shrink that down to a ship is to suffocate the very essence of life. So we are left with a stark conclusion. The chemical rocket is too heavy. The nuclear rocket is too slow. The antimatter rocket is too expensive. The light sail cannot stop. And the generation ship is a tomb in the making. The walls of the prison are complete. We have explored every physical escape route, and every single one has been blocked by the laws of nature. But there is one final layer to the prison, one final horror that we have not yet faced. We have talked about the failure of the machine. We have talked about the failure of the body, but we haven't talked about the failure of the mind. What happens to the human psyche when you lock it in a box for 1,000 years? What happens to a society that knows it is doomed to die in the dark so that a distant descendant can see a star? What happens when the middle generations, the ones who didn't choose the mission and won't see the end, decide that they have had enough. We are about to enter the realm of the psychological trap. We are going to look at mutiny, madness, and the collapse of the social contract in deep space. We are going to see that while metal can survive the void, meaning cannot. The sociology of the generation ship is the final nail in the coffin. If you thought the physical challenges were hard, wait until you see the mental ones. The universe doesn't just crush your ship, it crushes your hope. If you are ready to explore the darkness of the human mind in isolation, if you want to know why a generation ship is more likely to end in a civil war than a landing, verify your subscription. We are done with biology. We are moving to psychology. The airlock is sealed. The oxygen is running low. And the crew is starting to look at each other with suspicion. Like this video to keep the peace. For now. We have sealed the hull. We have calibrated the air scrubbers. We have accepted the slow decay of the biological support systems, but even if we solve the engineering problems of the generation ship, even if we create a perfect closed-loop ecosystem that recycles every atom of water and air for 1,000 years, we are still left with the most volatile component of the entire mission. We are left with the cargo. We are left with the human mind. The ultimate barrier to interstellar travel is not the Tsiolkovsky rocket equation, nor is it the laws of thermodynamics. It is the fragile, chaotic, and deeply terrestrial nature of human psychology. We are about to discover that while you can take a human out of Earth, you cannot take Earth out of the human. To understand the horror of a generation ship, we must strip away the romantic veneer of science fiction. In movies, the crew of a starship is a disciplined hierarchy, a military unit that follows orders and maintains a clear chain of command. But a generation ship is not a military vessel. It is a village. It is a city in a bottle. And cities have crime. Cities have politics. Cities have madness. The fundamental flaw in the concept of the generation ship lies in the 3 generations problem. The first generation, the founders, are the volunteers. They are the zealots. They stood on Earth, looked at the stars, and made a conscious choice to sacrifice their lives for a distant future. They have agency. They have purpose. They remember the blue sky and the smell of rain, and they carry that memory as a sacred flame. They are heroes in their own narrative. The final generation, the arrivals, are the inheritors. They are the ones who will wake up one morning and see a new sun filling the viewports. They will be the ones to walk on the surface of Proxima b. They will be the ones to justify the sacrifice. They have a destiny. But what about the generations in between? What about the middle generations? These are the people born in the void. They did not choose to leave Earth. They did not choose to go to the stars. They were conscripted before birth by the decisions of their grandparents. They will be born in a metal corridor. They will learn to walk on a vibrating deck. They will live their entire lives maintaining the air filters, scrubbing the algae tanks, and repairing the hull of a ship they did not build. Traveling to a destination they will never see. They are the maintenance staff of a dream that belongs to someone else. Imagine being born into a prison where your only crime was existing. Imagine being told that your entire life's purpose is to be a biological bridge, a genetic carrier for a future you will be dead for. This realization creates a psychological pressure cooker that no society on Earth has ever had to withstand. On Earth, if you hate your job, you can quit. If you hate your town, you can move. If you hate your government, you can protest or flee. On a generation ship, there is nowhere to go. There is no outside. There is only the ship. The ship is the world. The ship is God. This total confinement leads to a condition known as the solipsism syndrome. It is a psychological state observed in people living in artificial environments for extended periods, such as researchers in Antarctica or submariners. When your entire reality is artificial, when the light is LED, the air is recycled and the walls are metal, the mind begins to detach from reality. The outside world ceases to feel real. The universe beyond the hull feels like a simulation or a dream. The only thing that exists is the immediate, tangible environment of the ship. For the middle generations, Earth would become a myth. They would see videos of forests and oceans, but they would have no frame of reference to understand them. Wind would be a word in a database, not a sensation on the skin. Horizon would be a mathematical concept, not a visual one. They would develop a culture that is deeply introverted, possibly terrified of open spaces. If they ever did arrive at a planet, the sheer scale of the sky might drive them insane. This is the agoraphobia of the void, but the internal danger is far greater than the external one. A generation ship requires absolute totalitarian stability. You cannot have democracy on a lifeboat. You cannot have a vote on whether to open the airlock. You cannot have a strike by the water recycling engineers. If a critical system fails, everyone dies. Therefore, the social structure of the ship must be rigid. It must be a dictatorship of necessity. The captain is not just a leader, the captain is a king, or perhaps a high priest. This creates a fertile ground for social collapse. History teaches us that rigid, isolated societies almost always descend into paranoia, factionalism, and violence. Consider the mutiny on the HMS Bounty. A small crew, isolated in the Pacific, turned on each other over grievances that seem petty in hindsight. Now imagine that scenario, but the isolation lasts for 500 years. The most likely outcome for a generation ship is not a successful landing, but a civil war in a bottle. The middle generations will inevitably rebel. They will ask, why should we continue? A charismatic leader will rise up and say, Earth is gone. The destination is a lie. This ship is our home. Let's stop maintaining the engines and start living for ourselves. Let's turn the hydroponic gardens into pleasure parks. Let's stop sacrificing our comfort for the sake of great-grandchildren we will never meet. If a faction seizes control of the life support systems, they hold the rest of the ship hostage. Do what we say or we turn off the oxygen. The ship becomes a battlefield. But unlike a war on Earth, you cannot retreat. You cannot hide. And if you use heavy weapons, you puncture the hull and kill everyone. It is a knife fight in a phone booth. The fragility of the social contract is exposed when survival is a zero-sum game. And then there is the problem of cultural drift. Language evolves. Values change. Religion mutates. Over 1,000 years, English would evolve into a dialect unintelligible to us today. The original mission parameters, the constitution of the ship, would be interpreted and re-interpreted until they became religious dogma. The mission manual becomes the holy book. The earth becomes heaven, a place of infinite resources and blue ceilings that the ancestors were cast out from. The destination becomes the promised land. The scientific purpose of the mission would be lost, replaced by ritual. The crew might forget how to fix the warp drive or even what the warp drive is. They might continue to push buttons and turn levers because the manual says so, without understanding the physics behind it. We see this in cargo cults on Earth. On a generation ship, it leads to a primitive society living inside a high-tech shell they no longer comprehend. They are ghosts haunting a machine built by gods. We must also consider the population dynamics. To maintain genetic diversity, you need a starting population of at least a few thousand people. But the ship has finite resources. You cannot have a baby boom. You cannot have exponential growth. The population must be strictly controlled. One birth for every death. No more, no less. This means reproductive rights are abolished. The ship decides who breeds and when. Your partner is chosen by an algorithm to maximize genetic diversity. Your child is assigned a role before they are born. You will be a reactor technician because we are running low on reactor technicians. This is not a life. It is a sentence. It is a biological machine where human beings are just cogwheels made of meat. How long can a human soul endure that kind of crushing determinism before it snaps? History suggests not long. There is a terrifying precedent for this kind of breakdown. In 1973, a psychological experiment called the Stanford Prison Experiment showed how quickly ordinary people, when given power and placed in a confinement scenario, turn into sadists and victims. Now imagine that experiment running for 10 centuries. The guards and the prisoners are the same families generation after generation. A caste system would emerge. The bridge crew living in the upper decks, hoarding the best food and the best view. The engine rats living in the radiation-soaked lower decks, keeping the fires burning. The class war would be inevitable, and in space the poor have a weapon that the rich cannot counter-sabotage. A single wrench thrown into a turbine, a single valve opened at the wrong time, and the aristocracy dies along with the peasants. The mutually assured destruction of a generation ship ensures that any conflict becomes an extinction event. So the generation ship arrives at Proxima Centauri. The engines fire to decelerate. The hull cools. But who steps out of the airlock? Is it a team of bright-eyed explorers ready to catalog the flora and fauna? Or is it a tribe of pale, half-blind, genetically drifted religious fanatics who have forgotten that Earth ever existed? Or worse, is it a ship of the dead? A ghost ship, guided by an automated computer carrying the frozen corpses of a crew that destroyed itself 500 years ago in a war over water rations. The biological anchor is not just about the weight of water or the recycling of air. It is about the weight of history. It is about the fact that we carry our demons with us. We carry our tribalism, our greed, and our fear. And in the pressure cooker of a starship, those demons grow until they consume the host. This realization forces us to confront the Fermi paradox from a new angle. Perhaps the reason we don't see galactic empires is not because interstellar travel is physically impossible, but because it is sociologically impossible. Perhaps every civilization that tries to build a generation ship ends up building a floating asylum. They launch into the dark and then they go quiet. They implode. They turn into tombs. The rocket equation stops us from going fast, but the psychology equation stops us from going far. The mind is the limit. We are adapted for a world of horizons, of seasons, of unpredictable chaos. We are not adapted for the sterile, predictable, eternal monotony of the void. We go crazy when we are bored. And interstellar travel is the ultimate boredom, punctuated by moments of sheer terror. So is there any hope? Is there any way to break the psychological prison? Some futurists suggest that the only way to survive the journey is to stop being human. We must merge with machines. We must upload our consciousness into computers, or genetically engineer our bodies to hibernate for centuries. If we can sleep through the void, we bypass the madness. If we can become digital, we bypass the boredom. But then, are we still us? If the thing that arrives at the stars is a computer program or a genetically altered post, has humanity really succeeded? Or have we just sent a probe that thinks it is people? The answer remains written in the dark. The great silence continues. We are alone in our solar system, protected by the distance, imprisoned by the gravity, and defined by our fragility. We have now explored the limits of the machine, the limits of the body, and the limits of the mind. We have seen the traps laid by physics and by psychology. The picture is complete. The mathematical prison is not just a theory. It is a description of our reality. In the final chapter, we will bring all these threads together. We will look at the ultimate meaning of this quarantine, Why are we here? Why are we alone? And if we can never leave, what does that mean for the future of our species? We will look at the cosmic zoo hypothesis and the idea that our isolation is not a punishment, but a protection. We are reaching the end of the journey. The airlock is cycling. The final transmission is preparing to broadcast. If you are still here, trapped in the gravity well with us, verify your subscription. You are part of the crew now. The ship might be drifting, but the signal is still strong. Like this video to maintain fleet cohesion. The madness hasn't taken us yet. The final realization is approaching. We have reached the end of the trajectory. We have launched our rockets, ignited our nuclear pulses, unfurled our light sails, and sealed our generation ships. And one by one, we have watched them fail against the immutability of the universe. The chemical rockets were too heavy. The nuclear engines were too slow. The antimatter drives were too expensive. The light sails could not stop. The generation ships rotted from the inside out, consumed by biological entropy and social madness. The walls of the prison are not just standing, they are closing in. The Tsiolkovsky rocket equation, combined with the limits of biology and psychology, has created a quarantine zone around our star that is effectively impenetrable. This realization forces us to confront the most haunting question in all of astronomy, a question asked by Enrico Fermi in 1950. Where is everybody? If the galaxy is billions of years old, and if Earth-like planets are common, and if life arises naturally, then the Milky Way should be teeming with civilizations. We should see their megastructures dimming the light of stars. We should hear their radio chatter filling the spectrum. We should have been visited by their probes long ago, but we see nothing. We hear nothing. The universe is a ghost town. The silence is absolute. For decades, we have invented terrifying explanations for this silence. We feared the dark forest theory that civilizations hide because there are predators in the dark. We feared the self-destruction theory that intelligent species inevitably nuke themselves before they leave their home planet. But the rocket equation offers a simpler, cleaner, and more devastating explanation. The aliens are not hiding. They are not dead. They are just stuck. Imagine a civilization that arose 5 billion years ago on a super-Earth orbiting a red dwarf star in the Carina Nebula. They are intelligent. They are peaceful. They have mastered fusion energy. They have cured all diseases. They look up at the night sky and see our sun, a yellow dot in the distance. They dream of visiting us. They build their own version of the Saturn V. They derive their own version of the rocket equation. And they hit the exact same wall. They realize that to cross the gulf between their star and ours requires an energy expenditure that would bankrupt their civilization. They realize that their biology cannot survive the journey. They realize that their minds cannot endure the isolation. Physics is the same everywhere. Gravity is the same everywhere. Mass is mass. Energy is energy. The constraints that bind us bind them. The universe is not a continuous continent of civilizations waiting to be connected by a galactic railroad. It is an archipelago of isolated islands, separated by an ocean so wide and so stormy that no ship can cross it. We are not alone in the universe in the sense that we are the only life. We are alone in the sense that we are the only life here. We are solitary prisoners in separate cells tapping on the walls. But the walls are too thick for the sound to carry. This is the cosmic quarantine. It is a mechanism built into the laws of thermodynamics to prevent the contamination of timelines. It ensures that every civilization must solve its own problems. There is no cavalry coming over the hill. There is no alien fleet coming to save us from climate change, or war, or our own stupidity. There is no planet B waiting for us if we ruin Earth. The quarantine forces us to face the consequences of our actions. This sounds like a tragedy. It feels like a defeat. We are raised on stories of endless expansion, of Star Wars and Star Trek, where the galaxy is a bustling community. To be told that we are grounded feels like a betrayal of our potential. But there is another way to look at it. Perhaps the quarantine is not a prison but a sanctuary. If the rocket equation did not exist, if interstellar travel were easy, imagine the chaos. A single aggressive species could spread across the galaxy in a geological blink of an eye, consuming resources, destroying developing biospheres, and homogenizing the cosmos into a single empire. The barriers of distance protect diversity. They ensure that life on Earth has had 4 billion years to evolve in peace, without being trampled by a civilization that got a head start. The walls that keep us in are also the walls that keep the monsters out. And let us look at what we are trapped with. We often lament that we are stuck in the solar system, but the solar system is vast beyond comprehension. The distance from the sun to the edge of the Oort cloud is nearly 2 light years. That is a territory of influence with a diameter of 12 trillion miles. Within this territory, we have a fusion reactor, the sun, that burns with the power of 1 billion hydrogen bombs every second. It provides more energy in a single day than humanity has used in its entire history. We have the gas giants Jupiter, Saturn, Uranus, Neptune, huge reservoirs of hydrogen and helium, the fuel for our future. We have the asteroid belt, containing enough metal to build skyscrapers on every continent 1,000 times over. We have the moons of Jupiter and Saturn, Europa and Enceladus, holding oceans of water larger than our own. If we stop obsessing over the stars we cannot reach and start focusing on the worlds we can, the narrative changes. We are not prisoners. We are inheritors of a mansion we have barely explored. We have spent all our time in the nursery staring out the window at the neighbors' houses while ignoring the fact that we have 100 other rooms in our own house that are sitting empty. We could terraform Mars. We could build floating cities in the clouds of Venus. We could mine the asteroids and build rotating habitats, O'Neill cylinders that replicate the environment of Earth in deep space. We could build a Dyson swarm capturing the sunlight to power a civilization of trillions. We could live for millions of years without ever leaving the sun's gravity. We could evolve into a species that spans the darkness between the planets, a true solar civilization. The rocket equation allows this. It permits travel within the gravity well. It permits the trade of resources between Mars and Earth. It permits the slow, majestic dance of commerce across the interplanetary void. We can have a future of infinite complexity and wonder, but it will be a local future. It will be a story written in the ink of our own sun. This shift in perspective transforms us from conquerors to gardeners. A conqueror wants to expand, to take, to move on. A gardener wants to cultivate, to nurture, to stay. The rocket equation forces us to become gardeners. It forces us to realize that Earth is not a launch pad. It is a home. It is the only place in the known universe where we can breathe without a machine. It is the only place where rain falls, where plants grow, where life exists without a constant, desperate struggle against the vacuum. Tsiolkovsky was right when he said, "Earth is the cradle of humanity, but one cannot live in a cradle forever." But he was wrong about where we go next. We do not leave the cradle to wander the dark forest. We leave the cradle to expand the house. We build new rooms. We turn the solar system into a home. Ultimately, the limit of human travel is the limit of our biology, dictated by the math of our propulsion. We will likely never leave the solar system. We will never walk on the surface of a planet orbiting another star. We will never meet an alien face to face, and that is okay. Because the solar system is enough. It has canyons deeper than the Grand Canyon, oceans hidden beneath ice, storms that have raged for centuries and mysteries that will take us 1,000,000 years to solve. We have not even begun to understand our own backyard. So the next time you look up at the night sky, do not feel trapped. Do not feel small. Feel protected. The vast distances that separate us from the stars are the same distances that protect us from the chaotic violence of the universe. We are in a bubble of stability, a rare oasis in a hostile desert. The silence of the void is not a sign of emptiness. It is a sign of peace. We are the prisoners of Kaluga, sitting in our wooden house dreaming of the infinite. The math says we cannot go, but the math cannot stop us from looking. And as long as we can look, as long as we can wonder, as long as we can build telescopes to see the beginning of time and computers to simulate the end of it, we are not truly trapped. We are simply home. This has been a journey into the hard limits of reality. We have stripped away the science fiction and looked at the cold steel of the rocket equation. We have seen the fuel tanks, the nuclear pulses, and the dying biospheres. We have seen the boundaries of our cage, and in seeing them, we have found our freedom. Freedom from the impossible expectation of conquest. Freedom to appreciate the fragile, rare, and beautiful existence we have right here. If this deep dive into the physics of our confinement has shifted your perspective, if you feel the weight of the equation pressing down on your imagination, then our mission is complete. The universe is darker and heavier than we like to admit, but there is a strange comfort in knowing where the walls are. We are star stuff, contemplating stars we can never reach. That is our tragedy, and that is our glory. This is the end of the mathematical prison, but it is not the end of the inquiry. There are other prisons to explore: the prison of time, the prison of consciousness, the prison of reality itself. If you want to continue exploring the shadows of science, the theories that keep us awake at night, make sure you are subscribed to Nocturnal Science. We are building a community of the curious, the sleepless, and the wondering. Leave a comment below. If you could leave Earth on a one-way trip to the stars, knowing you would never reach the destination but your descendants might, would you go? Or would you stay and tend the garden? The algorithm does not sleep, neither do we. Like this video to signal your presence in the dark. The rocket engines are cooling down. The silence is returning. But the mind is just waking up. Sleep well.